All right, whoops. Today we're going to talk about the mole concept. The mole concept is a central sort of idea in chemistry that basically allows us to do quantitative calculations on chemical reactions. Chemists, it turns out, are actually mole people. Now, the one mole person we're going to be talking about is this guy. Gentleman's name is Avogadro. And yes, that's what he looks like. We're going to see exactly what he found and the ramifications of everything in terms of chemistry. So, we have pointed out that a single copper penny would contain 28 sextillion atoms. If you want to do calculations based on the number of particles or molecules you're dealing with huge numbers like this would be terrible, okay? So what Avogadro did was define a quantity, a unit called a mole. A mole, it turns out, has 6 times 10 to the 23rd particles, and this number, 6 times 10 to the 23rd, is what's known as Avogadro's number. Now, it's based on his observations, kind of a surprising observation for the time, that equal volumes of any gas whatsoever, had the same number of particles. Now, if you think about what a gas is, there's so much space in between the particles that that's probably why this whole thing works. Nonetheless, he was able to calculate that if you had 22.4 liters of any gas, the mass of that was equal to the formula mass of the compound. Now we'll talk about what this is in a second. And he also was able to show that the 22.4 liters contain 6 times 10 to the 23rd particles. If we have a mass of any substance that's equal to its formula mass, what this says is that that mass, that lump of stuff, will contain 6 times 10 to the 23rd particles. This is called the molar mass. Now, what is a formula mass? If you look at the periodic table, we have an average mass for each of the elements, based on number of isotopes and whatever. If we sum up the average masses of all the atoms in the molecule, we get the formula mass in atomic mass units. Now, typically we don't indicate AMU, but we can. For example, the amino acid glycine looks something like this. Now, we've seen molecular models. The blue is nitrogen, red is oxygen, black is carbon, and the white is hydrogen. So in this molecule, we have 2 carbons. We look at the periodic table. Each carbon weighs 12.01. So to calculate the formula mass, we simply do that. We have 5 hydrogens. Each one is 1.008. We have 1 nitrogen at about 14, and 2 oxygens at about 16 each. We multiply all this out, we add it together, and we get 75.07 atomic mass units. That's the formula mass. Now, if we want the molar mass, all we do is take this number and express it in grams. So if we had 75 grams of glycine, it would have 6 times 10 to the 23rd glycine molecules. Now that's kind of an interesting sort of concept. Think about it. This balloon has a volume of 22.4 liters filled with oxygen. Oxygen is O2, so this is 32 grams of oxygen. This little lump of copper down here is 63 grams. 18 grams of water. Chalk is calcium carbonate. This is 100 grams of it. Basically, if you wanted to react, say, copper with oxygen, we would know if you wanted to react 1-to-1, you would want 32 grams of oxygen and 63 grams of copper. They both contain exactly the same number of molecules or atoms. Isn't that amazing? Well, today they define, based on carbon-12, the isotope, exactly 12 grams has 6 times 10 to the 23rd atoms, and in fact, they go one further and ignore the number and say that Avogadro's number is actually 12 grams of carbon-12. 6 times 10 to the 23rd is what we're looking at. Now it's important to realize that the mole is just a number. It's a unit. And if you have any doubts, there's a song.
Is an animal that burrows in the ground, or a spot on your chin that you gotta shave around. But there's another kind of mole of interest to me. That's the kind of mole they use in chemistry. A mole is a unit, or have you heard, containing 6 times 10 to the 23rd. That's a 6 with 23 zeros at the end. Much too big a number to comprehend. Now say you had a mole of pennies to distribute round the world. Give to each of the 5 billion grown-ups, boys and girls. There wouldn't be a single soul down and out of luck, 'cause everybody in the world would get $1 trillion. Or say you had a mole of paper and stacked it toward the sky. Paper's awful thin, but that pile would get so high, you'd reach up into outer space. In fact, I think you'd find it'd go up to the moon and back 80 billion times. And the mole is a unit, or have you heard, containing 6 times 10 to the 23rd. That's a 6 with 23 zeros at the end. Much too big a number to comprehend. Now suppose a mole of marshmallows fell upon the planet. Over each square inch of land and sea, you think that you could stand it? That layer would be 12 miles high and of course block out the sun. We're talking close to 5 million trillion tons. Well, maybe we could save ourselves if we all started eating 1 marshmallow each second. Not 2, 'cause that'd be cheating. With 5 billion people munching, how long you think it'd take? 40 million years, and that's without a bathroom break. And the mole is a unit, or have you heard, containing 6 times 10 to the 23rd. That's a 6 with 23 zeros at the end. Much too big a number to comprehend. But say you had a mole of atoms. Would the pile be immense? Should I say the answer now or leave you in suspense? Well, atoms are so very, very small, you understand. You could hold a mole of atoms in the palm of your hand. So shake a little sugar in the middle of your palm. Now you don't want to spill it, so try and stay calm. You hardly can imagine and barely realize there are more atoms in that sugar than stars up in the sky. And the mole is a unit, or have you heard, containing 6 times 10 to the 23rd. That's a 6 with 23 zeros at the end. Much too big a number to comprehend.
Right, yes, that was cute. Mole Day, what is Mole Day? It's coming up actually. October 23rd. Get it? 10/23? Okay. Um, we talk about numbers like 10 to the 23rd. We'll do it a lot. And yeah, this thing said you pile up paper to the moon 80 billion times, etc. But it's really hard to understand just how big that number is. So a meter is about like this, right? If we start off, well, shoot, I forgot this slide. This is in fact 7.5 grams of glycine, and that's 1 mole. Just so you know, 1 mole of atoms really does fit in your hand. All right, as I was saying, 10 to the 23rd is a huge number. I'm going to start off here looking at a leaf. I'm going to back off 1 meter, then back off 10 meters, and 100 meters, and 1,000 meters, and keep going until we hit 10 to the 23rd meters. What do you think it's going to look like? It's surprising, I think. So let's start. Oh, here we're looking right at the leaf. We back up. Yeah, it's a leaf. That's a meter away. It's a tree. Still a tree. We're 10 to the 5th now. Oh, it's in Florida. It's on Earth. At 10 to the 8th, there's the Earth and the Moon. 10 to the 10th, 10 to the 11th, 10 to the 12, 13. At 10 to the 14, or 10 to the 15, that's our entire solar system. That's the Sun. 10 to the 17, can't see it anymore. Now we're up in the Milky Way. Yeah, we're there somewhere. At 10 to the 22, there's the Milky Way. 10 to the 23, that little furry blob right there, that's the Milky Way. 10 to the 23 is an absolutely huge number. But it's a unit. If we're talking about bagels, you go out and buy a dozen bagels. A dozen is a unit, isn't it? Think of a mole just like a dozen. It's just a very, very large dozen. This is 6 times 10 to the 23rd. There are more decimal or digits after the decimal. Typically, we use 6.02 in class. 3 significant figures. If we had a mole of bagels, it would be 6 times 10 to the 23rd bagels. You could have a mole of pigs, a mole of anything. So let's do our first silly problem. I have 66 dozen dogs and they each have 4 legs. How many legs are we talking about? Well, we're going to do this using the given ratio find thing, right? Our given is going to be our 66 dozen. We know that there are 12 things in a dozen, and we know that there are 4 legs on a dog. So we start off with our given. First thing we're going to do is multiply this by 12 things in a dozen, making sure dozen is in the denominator. Likewise, we have to put dog in the denominator. 4 dogs, 4 legs, 1 dog, whatever. Dozens and dogs cancel. 66 times 12 times 4 gives us legs. Do the simple math. 3,168 legs. Okay. Now we're going to do exactly the same problem, but instead of 66 dozen, we're going to have 66 moles, which means that our ratio isn't 12 to 1, it's 6.02 times 10 to the 23rd to 1. 66 moles of four-legged dogs. We know there are 10 to the 23rd things in a mole, and again, 4 legs in a dog. So we start off with our given. Next, we put in things in a mole. So mole is in our denominator, and 4 legs per dog. We cancel. Calculate this out, 1.589 times 10 to the 26 legs. If we look at our numbers here, we have 3 significant figures. This is a definition for a four-legged dog that has 4 significant figures, so we'll round this to 3. 1.59 times 10 to the 26. It's just a big number. It's a unit. All right, let's do a real problem. A mole of hydrogen contains 6 times 10 to the 23rd hydrogen molecules. If we have half a mole, how many molecules do we have? I would get it for you, but I'd probably fall over. We know there are 6 times 10 to the 23rd molecules in a mole. We know that we have half a mole, so that's our given. We'll start off with our given. In our ratio, molecules per mole, mole in the denominator. Moles are going to cancel here. And we're left only with molecules. Do our calculation. 0.5 times 6 times 10 to the 23rd is 3 times 10 to the 23rd. That's why I wanted you guys to do the exponent tutorial, to really get used to using big numbers on your calculator. Any question? Well, we use moles lots and lots of different ways in chemistry. One thing that we're going to do is use something called a mole ratio, describing a compound. It's actually a fairly simple concept. If we had carbon dioxide and we had 1 mole of carbon dioxide, that would contain 1 mole of carbon and 2 moles of oxygen. Basically, it's just the coefficients in CO2. If we have ethanol, this is the alcohol of consumption. We have 1 carbon, 2 carbons. We have 6 hydrogens and 1 oxygen. The mole ratio would be 2 carbons, 6 hydrogens, 1 oxygen. Simply describing the compound in mole terms. All right, we have something with 2 moles of iron, 3 moles of sulfate. What is it? Again, we're simply talking about the subscripts here. 2 moles of iron, 3 moles of sulfate. Here's what we're dealing with. We need a 2 here, and we need a 3 here. All right, we have a test coming up, don't we? What is this thing called?
Was it ionic molecular?
It's an ionic compound, yes. What's the name of it?
Iron sulfate.
Sulfide.
Iron what sulfate?
Iron 2.
Iron 3. Iron 3.
Iron 3 sulfate. Remember, every sulfate is going to be a -2. That's 6 negatives. Each iron must be a +3. Remember, no space between the Roman numeral and the iron. One more, simple one. Here we have a compound, 3 moles of carbon, 6 moles of hydrogen, 2 moles of oxygen. We do our CHO. Our first subscript here is number 3. Next we have 6 for hydrogen and 2 for oxygen. It's simply the mole ratio for a mole of the compound. Now we're going to use this in several types of problems. Let's just see how we do this. If I say I have 1,000 moles of ammonia in H3, and I'm asking you how many atoms of hydrogen are there in our 1,000 moles? What you have to do is simply look at ammonia and come up with the mole ratio of hydrogen to the compound. There are 3 hydrogens in 1 molecule of ammonia. There are 6 times 10 to the 23rd molecules in a mole. That's 2 ratios, right? Just like dogs in dozens. So we'll start off with our given, 1,000 moles. We have 6 times 10 to the 23rd molecules in a mole, so mole in our denominator. We have 3 hydrogens in 1 molecule, so molecule in our denominator. We simply multiply 1,000 by 6 times 10 to the 23rd times 3, 1.8 times 10 to the 27. Now, you know, I use slides here, right? And I spend a great deal of time making them. And so they always turn out right. Right? Almost. What if you were doing this problem and you simply wrote your ratio wrong? Would you like say, oh my goodness, start all over? No. Here we have mole, and we have mole in the numerator. That doesn't work. It has to be in the denominator. If you do something like this, just say, oh shoot, and turn the thing upside down. Perfectly valid mathematical operation. Just flip it over. Any questions? Let's do another one. Let's do carbon tetrachloride. We have 0.05 moles. We're looking for how many chlorine atoms there are. Go ahead and see if you can set the thing up. Our given here is going to be our 0.05 moles. We have two ratios. One is 10 to the 23rd molecules in a mole. And the second one is 4 chlorines in 1 molecule. We have set it up properly. Moles cancel, molecules cancel. Simply multiply it out. 0.05 times 6 times 10 to the 23rd times 4. 1.204 times 10 to the 22nd. Again, 3 significant figures here. We round this to 1.2. Any questions? It's not that difficult a concept to grasp. It's just a big number. We have 3 times 10 to the minus 9 moles of a gas. Doesn't matter which gas, does it? How many particles is that? Again, we're going to use Avogadro's number. And our given is going to be the number of moles. Just go ahead and set it up. Start off with our given. Mole has to be in our denominator. And we're left only with particles after we cancel. Now, let me just point this out while I'm thinking about it. I just canceled moles and mole, didn't I? They're the same thing. Sometimes we'll just do mole and MOLs, whatever, it doesn't matter, they're all moles. All right, 3 times 10 to the minus 9 times 6 times 10 to the 23rd, 1.97 times 10 to the 15. Still a huge number, isn't it? Now, we're going to have 4 tutorials for this chapter. I just wrote and added the last one, just so you'd have an extra shot at 5 more points. I want to show this one first, just a couple simple problems, because it uses mole ratios. So let's just do that. Mole mass relationship is what it's called, and we'll talk about it later as well. We have a sample of KNO2. What is that?
Potassium. Is it
Nitrite. Right. Nitrate is a parent. NO3. Nitrite, 1 oxygen is gone. They're both minus 1. We have 1.1 moles of potassium in there. How many moles of potassium nitrite are there? Well, this is actually very simple, isn't it? We need to do the mole ratio of potassium to potassium nitrate. And that is 1. We have moles of nitrite, moles of potassium. It's simple, 1 to 1. So we're going to take our given, multiply it by our ratio, and the answer is 1.11. I told you it was simple. Let's do one more, and again, we're going to come back to this later for some more complicated ones. Water, H2O. We have 1.34 moles of hydrogen. How How many moles of water is that? Well, look at water and say, what is the mole ratio of hydrogen to water? There are 2 hydrogens in every water. The only thing you have to be careful of is this going to be a ratio of 2 or of 1/2? So you have to look at the units of your given. We have moles here, so we need moles of water on top, moles of hydrogen on the bottom. Gonna simply multiply that by our given. 1/2 is our ratio, and we get 0.671. So, like I said, there are 4. This is probably the trickiest of them. That's why we're going to come back and do it again later. Let's look at some old exam questions. Calculate the number of moles in 17.8 grams of magnesium hydroxide. That's MgOH2. Every hydroxide is -1. Every magnesium is +2. Well, okay. We have a given here, don't we? But what do we use for a ratio? The molar mass here is a ratio, isn't it? 58 grams divided by moles. That's a ratio. So, we are given the mass. Our molar mass is our ratio. We would start off with our given. In our ratio, grams has to be in the denominator, so we flip this upside down. The grams will cancel, and we get 0.305 moles. Again, 3 significant figures. Now, what we have done here can be summarized very simply. We have taken a mass and we have essentially divided it by its molar mass, haven't we? That gives rise to something you should always remember. Mass divided by molar mass gives you moles. This is one of those things you say at night before you go to sleep. Laying there in bed, mass divided by molar mass is moles. Good night. Any questions? Don't forget it. All right, another problem. 6.02 times 10 to the 23rd molecules in a mole. 10%. If we have 10% of a mole, how many molecules will we have? Now, just like the last one, that can be our given, but what do we use for a ratio? Well, think about how you do a percentage. You take a number, divide it by 100, and then multiply by 100. This is really 10 divided by 100. That's a ratio. So we can use it simply. Here's our given. Our ratio is 10 to 1. Simply multiply, or actually divide by 100, and we get 6 times 10 to the 22 molecules. Now, I'm sure everybody has noticed that nothing lit up here. This is 6.02 times 10 to the 20. That's not the same. Certainly not 1 times 10 to the 20. 0.6 times 10 to the 22. That's not quite good form, but you would move our decimal one more point and give us 21. That's not right. This is the dreaded none of the above. All right, one more here. We have 21.509875 grams of CO2. How many moles is that? Once again, we have a mass and a molar mass, don't we? We're going to take our mass, divide it by our molar mass, and get moles. Go ahead and do it. I'm going to write this out the long way. Take our given, multiply it by this is a ratio with grams in the denominator. So 21.5 whatever divided by 44.01 gives us what? Well, on your calculator, this is what you get. Now we have 4 significant figures here, don't we? 44.01. How do we round this? Does the 7 here round to 8, because it's 5? Or does it round down to 7?
You run through.
Round.
The rule is, if your number ends in exactly 5, and that's why I had to do such a strange number here, if it ends at exactly 5, you round even. That means half the time it goes up, half the time it goes down. If it ends at exactly 5, this becomes an 8. Any questions? All right. This was an actual test question. I wanted students to, first of all, calculate a formula mass for methane, and then tell me how many moles of methane there were, or how many grams of methane there were at 1.03 moles. Okay? So, methane is 1 carbon, 4 hydrogens. Quickly determine the molar mass. We're going to take carbon at 12.011. We're going to take 4 hydrogens at 1.0079. Multiply them all together. And we get 16.0426 grams per mole. That's our molar mass, grams per mole. All right, so we're looking for mass. That's our thing we're trying to find. We know we have 1.03 moles, and this is going to be our ratio. multiply the given by the ratio with moles in our denominator. Something like this. We want moles in our denominator. We want grams in our numerator. Fill in the numbers, 16 and 1. Simply multiply 1.03 times 16, and we get a big number. Now, how many significant figures do we have?
6.
Well, we have a lot here, don't we? Only 3 up here. So, we'll round this to 3. That makes it 16.5. Any questions, guys? All right, it's time for another tutorial. This is one that everybody loves, kind of like significant figures. It's a table, and it looks something like this. You're given 2 out of 3, and you simply type in the missing. Okay, we could do that, right? We can do that. On your exam, I can promise you that you will get a table looking something like this. Where do I get the question? I go to Chemistry Online, hit New Problem, and transcribe the numbers. Great way to practice. So, we're looking for our molar mass. We know a mass and we know the number of moles. What is molar mass? It's simply mass divided by moles. So we take our mass, 104, divided by 1.03, and we get 100 grams per mole. Told you you'd like this one. Here we have mass missing. We know our molar mass, we know moles. If molar mass is mass divided by moles, then mass is simply going to be moles multiplied by molar mass. So we take our number of moles, 0.88, multiply by the molar mass, 186, and we get 163. Any questions? Well, this is mass, molar mass 1. There's a 2, and it's just as simple, except instead of being a table, it's a word problem. That sends chills down your spine, I'm sure. But it's really simple. Here we have our mass. Here we have our molar mass. We don't know moles. But we do know something, don't we? We know mass divided by molar mass gives us moles. Told you it'd be useful. Mass divided by molar mass is moles. We take our mass, 87, divided by 63, and we get 1.38 moles. Let's do another one. Again, we're looking for the mass in grams. We know the number of moles of lead. and we know the molar mass of lead. So we're looking for mass, aren't we? Mass is going to be simply moles multiplied by molar mass. Take our number of moles, take our molar mass, multiply them together, we get 19.9 grams. Now, this tutorial also has a cute feature. They're algorithmic, so the wording and things like that can change easily. And I have it so that every now and then it will ask you a question like this. We have 29 grams of an element. That 29 grams is 2.698 moles. What's the element? Well, in order to do that, all we have to do is determine the molar mass of the element, right? And then look at our periodic table. How do we get molar mass? Mass divided by moles, grams per mole. Mass divided by moles is our molar mass. We have 29 grams, 2.7 moles, 10.8 is our molar mass. Now on the exam, everybody gets a periodic table that looks something like this. There it is. And we're looking for an element with an average atomic mass of 10.8. Well, 10.8, so it's going to be close to the top. We have 9.0, 10.8, 12.0. Oops. 10.8 is boron. And we simply put B in our cell, and we get it right. Now on Blackboard, you have a mix of both types of questions. Some will be write the symbol, and some will be numeric. Okay? Just make sure you have a periodic table handy when you do the Blackboard test. This is an old exam question. We have 10 to the 23rd or 10 to the 20 molecules of chlorine. Chlorine is diatomic, so it's CO2. Average atomic mass, 70.9. What is the mass of this sample? Well, that would be simple to do if we knew how many moles we had, right? But we do, because we know how many molecules we have, and we know how many molecules there are in a mole. So, we know the number of molecules, we know molecules per mole, and we know a molar mass. Let's start off with our given. That's going to be molecules of chlorine. Now, we have molecules as our unit here. So that means this ratio has to have molecule in the denominator. So we write it this way. 1 mole is 10 to the 23rd molecules. Next, we have our molar mass here. This is going to have mole in the denominator because we have mole up here. So let's write our second ratio as 70.9 grams per mole. Let's check to make sure everything cancels. Molecule, molecule, mole, mole. And we're left only with grams of fluorine. Do our calculation. 10 to the 20 divided by 10 to the 23rd multiplied by 70. We have 0.011777, but only two significant figures. So we round it to what? 0.12. Any questions? All right, let's return to the mole mass formula tutorial and just do a couple more sophisticated problems. Here we have lithium and a nitrogen. Would that be ionic? Absolutely. Lithium's a metal. Would we use a multiplier? No. We would simply call it lithium nitride. All right. We have 1.9 moles of lithium in there. How many grams of lithium nitride do we have? Our mole ratio is going to be 3 lithiums for every nitrogen, right? Our given is 1.9 moles of lithium. So we want lithium in our denominator. Mole ratio, 3 moles of lithium, or 1 mole of lithium nitride is 3 moles of lithium. So we're at 1/3. We're going to take our ratio and our given, multiply them together, and get moles of lithium nitride. But there's more to it, because we need a mass. Multiply this by the molar mass, again, moles multiplied by molar mass gives us mass. Simply multiply it out, 22 grams of lithium nitride. So these are more sophisticated problems. There is a tutorial containing a mix of fairly simple ones and fairly fancy ones. Let's just do one more quickly. Here we have cobalt and oxygen. Is it ionic or molecular? Cobalt is a metal. It's ionic. We don't use multipliers, simply cobalt oxide, but because it's a transition metal, we have to put in the charge. What is it? Cobalt 3 oxide. Crisscross. All right. We have 3 moles of cobalt in every cobalt 3 oxide. Or 2 moles, I'm sorry. Our ratio here is 2 to 1. We have our given, which is moles. Multiply them together, we get moles of cobalt. We look up its molar mass, which is hidden by this, and we get 70 grams of cobalt. All right, there's one more, but I'm going to skip that. And instead, move ahead to another way that we use moles and mole ratios. When you do a chemical analysis, what you wind up with for a compound is a mole ratio. we're going to see how we can do this and get percentage composition. All right. If we had HCl, in Chapter 8, we will call this hydrochloric acid. We could also call it hydrogen monochloride. The mole ratio here, 1 hydrogen in every HCl, right? That's simple. But if we wanted to talk in terms of mass, what is 1 mole of hydrogen in terms of mass? 1.008. What is the molar mass of HCl? You simply calculate it, add it up. 1 gram of hydrogen, 35 grams of HCl. This is called a mass ratio. What we have done here is taken a mole ratio, simply expressed it in terms of molar mass for each, 1 gram of hydrogen, 35 grams of HCl. All right. Well, this is a numeric ratio, isn't it? When you get something like that, you really want to divide it, don't you? What would happen if we divided these together? We would get the mass of hydrogen for a mass of HCl. 0.02. Now, if I asked you the question, what's the percent by mass of hydrogen and HCl? You would simply take this ratio, multiply it by 100, and you say 2.84% by mass. That's the mass composition. Okay. Calcium fluoride, CaF2. What's the percentage of fluorine? First thing you do is write a mole ratio. We have 2 fluorines in every calcium fluoride. Now we look at our periodic table. Fluorine is 19. We calculate the molar mass of CaF2 and it's 78. Therefore, we have 2 fluorines at 19 each. 1 calcium fluoride at 78. 2 at 19 each, divided by 78. When you have a coefficient like this, a subscript, simply multiply the molar mass by that subscript. We calculate this out, we get 0.48. Again, if the question is, what's the percentage? Multiply this by 100, 48.67%. All right, percentage of oxygen in this stuff. Once again, exam is in 2 weeks. What is this stuff? SC. There it is. Scandium, yeah. Okay. ClO3, we remember, is chlorate.
You said the exam is in 2 weeks, so it's not next Monday?
It's not what?
It's not next Monday?
Nope.
So are we doing chapter 5 as well?
We just write scandium, and it's scandium 3. Because scandium is a transition metal. We have 3 chlorates. That means scandium has to be +3. Next week we have the sample. We'll talk about this at the end. Next week we have sample exam. Then after that we have the real. So 2 weeks. We'll talk about that in a minute. All right, so this is scandium 3 chlorate. Let's see. Oxygen is 15.999. We have how many oxygens? 3 times 3, 9. 9 moles of oxygen in every mole of scandium 3 chlorate. We have 9 oxygens at 16 each. 1 scandium chlorate at 295. The mass ratio is this. Simply multiply it out, and we get 0.488. We're dealing with actually 4 significant figures, aren't we? Well, I'm close though, 48%. One more way we could do this, calculate the mass of fluorine in 454 grams of magnesium fluoride. This is a pound. So we have a pound. How much fluorine is in that pound? First thing we have to do is do our percent composition. Then multiply that by the molar mass of fluorine. So, fluorine is 19. Magnesium fluoride is 62. We have 2 fluorines for every MgF. That's our mass ratio. Multiply it out. Well, okay, we could multiply this out. Or what I did here, and I forgot, was this is a ratio, isn't it? We don't have to do it in 2 steps. We can do it in 1 step. So here's our given, our 454. We'll use this guy as a ratio. Now we just have to multiply 454 times 2 times 19 divided by 62 to get grams of fluorine. Turns out to be 276. All right, so this leads us up to the last tutorial for this chapter. And this is percent composition. What is this stuff? That's nickel. Nickel is a transition metal. We need to show the charge. ClO, missing 2 oxygens, hypochlorite. Each of these is a -1, so the nickel is +2. Nickel, 2 hypochlorite. All right. This is the molar mass of nickel hypochlorite. What's the percentage for each of the elements? We look at this, we say, okay, our molar mass, first of all, our mole ratio, 1 nickel for every nickel hypochlorite. One nickel for every nickel hypochlorite. Ratio is simply 1. 58 divided by 161, 36.3. Chlorine. How many chlorines do we have? 2. So it's going to be 2 times 35 divided by 161, or 44%. We have how many oxygens? Also 2. 2 times 16 divided by 161, 19%. Now, if you note, these don't add up to 100, do they? That's because of, well, I'm not a great programmer, I suppose. Somebody once was doing a tutorial, did 2, and said, I'll just subtract from 100 and get the last one. Well, that works sometimes, but not always. Just go ahead and do it. It's a rounding error, but whatever. Just do it. ClO2 is what? If ClO3 is chlorate, ClO2 is chlorite. Calcium, not a transition metal. So it's simply calcium chloride. All right, 1 calcium for every calcium chloride. 1 divided by 175, 23. Chlorine, we have 1, 2 chlorines. 2 times 35 divided by 175, 40%. We have 1, 2, 3, 4 oxygens. 4 times 16 divided by 175, 36%. Any questions? All right, let's end this on a nice, simple descriptive note, okay? We looked at molecular models. We did glycine earlier. This is a ball and stick version of glycine, right? We made it. 2 carbons, 1 nitrogen, 2 oxygen, 5 hydrogens. This is called a space-filling model. Space-filling model tells you what the molecule actually looks like. We draw these little spheres at about 90% of the electron cloud. So it's a pretty good indication of what it looks like in real space. This and this are on exactly the same scale. So it's much bigger than you would expect it to be. The colors, kind of the standard sorts of colors. Carbon is gray, hydrogen is white, oxygen is red, nitrogen is blue, and here's our guy. For other elements, chemists tend to try to mimic what the element looks like. We'll do 2 things at once here. I've mentioned diatomic elements. We're talking about fluorine, talking about bromine once, oxygen, nitrogen. These are 2 atoms stuck together, covalent. Okay? Hydrogen, we said, was basically whitish. Nitrogen was blue, oxygen red. For fluorine, fluorine is actually kind of a yellowish sort of color. Chlorine is green. Bromine is brown, iodine is purple. So when you're putting together molecular models, you kind of try to come up with something that looks like the element. We talked about formulas and formula mass. The molecular formula is basically just a list of all of the things that are in a given molecule. For glycine, we have 2 carbons. We have 1, 2, 3, 4, 5 hydrogens. We have 1 nitrogen, and we have 2 oxygens. If we were to write this out, the simplest molecular formula would be something like this: C2H5NO2. The only problem with this is it gives you no information at all as to what glycine looks like. So there are other ways to write molecular formulas that are much more descriptive. We could just base it on the model here. Say we have a nitrogen that's attached to 2 hydrogens, H2N. That's attached to a carbon that has 2 hydrogens, CH2. And that's attached to a group with a carbon, 2 oxygens, and a hydrogen, COOH. Now, if you really want to be very descriptive, you can do what's called a Kekulé structure. In a Kekulé structure, you show the atoms and all the covalent bonds. So it's basically just like our model. We have a nitrogen with 2 hydrogens, a CH2, a carbon that's doubly bonded to an oxygen, and an OH. It's a pain to write, but it tells you absolutely what the molecule looks like. You will see a mixture of all of these. They're simple. All right, I said a while ago that the reason we care about mole ratios is that when we do chemical analysis, what you wind up with is a mole ratio. For example, empirical formula is the lowest whole number ratio of elements in a compound. This is glucose. We have a ring of carbons, we have a bunch of hydrogens, we have a bunch of oxygens, C6H12O6. If we take the lowest whole number ratio here, there are, for every 1 carbon, there are 2 hydrogens and 1 oxygen. It is CH2O. That's the empirical formula. If you did an analysis on glucose, the result you would get back from the lab is CH2O. Now think about this for a second. Glucose is a sugar, isn't it? H2O is water. What do we call sugars? Carbohydrates. That's where that comes from. The problem with an empirical formula is that it doesn't tell you what the molecule looks like. For example, this is acetic acid. It is the acidic component of vinegar. It has 2 carbons, 2 oxygens, 4 hydrogens. Lowest whole number ratio, CH2O. Carbohydrates are kind of neat. As I just said, sugars are basically 1 carbon to 1 water. Turns out that chemically we can separate these. This again is glucose, CH2O. If we take a little beaker here of glucose and we add concentrated sulfuric acid, it will catalyze the breakdown of this into water and carbon. Kind of neat. You do this very, very carefully. Concentrated sulfuric acid will eat your skin in seconds. Stir it up. After a minute or two, it starts to turn ugly. Then it starts to get hot. As it gets hot, the reaction proceeds. We get water in the form of steam, and we get the carbon from the sugar as this column of pure graphite. Kind of neat. Any questions? Again, carbohydrates, empirical formula, CH2O. All right, let's just write a couple of empirical formulas. Acetylene. Use this in acetylene torches, welding, and stuff like that. 2 carbons, 2 hydrogens. Lowest whole number ratio, CH. Acetylene features a carbon-carbon triple bond. If we look at this in a space-filling model, it's something like this. This is our triple bond. The nice thing about a space-filling model is that, yeah, you can see what it looks like, right? The bad thing is you cannot see a triple bond there. Benzene. Benzene is a marvelous solvent. When I was a child, we used to wash everything in benzene, including our hands. It has since been found to be a hepatocarcinogen, and we're not even allowed to have it on campus. So much for washing your hands, huh? We have 6 carbons, 6 hydrogens. Again, the empirical formula is simply CH. This is what benzene looks like. Kind of a neat molecule, single and double bonds, but they aren't really. In organic chemistry, you will learn that this is aromatic, it's called. Has nothing to do with how it smells, but has to do with delocalizing the electrons. In a space-filling model, it looks beautiful, something like this. Here's our double single bonds and our hydrogens around the rim. For water, H2O. Lowest whole number ratio, H2O. And hydrogen peroxide, H2O2. Empirical formula is simply O. All right, thus into chapter 4. Now, next week, we are going to do the sample exam in class. What you need to do is find the sample exam on Blackboard, next week's folder. Print 2 copies. Work one of them. The one that you work, you hand in, and you get 10 points extra credit. Okay? The other one, we will go through the questions one at a time and answer any questions you may have. So use it just to take notes. After this lecture, quiz number 1 will come online magically. It's on Blackboard. It's worth 20 points. You must complete this before we take the real exam. This coming Wednesday, we will have lab number 4. We added 4 tutorials today. This is our full list. Today we have mole mass conversions, 1 and 2, mole mass formula, and percent composition. You must complete these before we do the exam, because the day of the exam, actually at 11 o'clock, it disappears forever for Blackboard. Okay. Have a good day.